Well, thank you to the organizers for inviting me. I was happy to be able to come. As she said, I'm going to talk about quantum morphisms, so specifically quantum homomorphisms and quantum isomorphisms of graphs. I think one of the interesting thing about the topic is that it sort of kind of connects to quite a few different areas in mathematics. And it's based on sort of ideas from quantum information, but you don't really need to know much quantum information to do anything with it. So I don't know a huge ton of quantum information, and I manage okay. But I will give the introduction in terms of the kind of quantum information background, but then we'll quickly move away from there. Hopefully by the end of the this first lecture, we'll sort of just have a nice algebraic formulation for quantum homomorphism. All right, so let's start with just a classical homomorphism. So what's a homomorphism between graphs? So I don't really know what the background for everyone is, so I just assume that no one knows what a homomorphism is. So if I have a function between the vertex sets of two graphs, then this is homomorphism if it preserves adjacency. Right? So I use this tilde notation to denote that U and V are adjacent. And this is going to be undirected simple graphs. Okay? So if I input two vertices that are adjacent, I have to get out two vertices that are adjacent. It doesn't need to be injective or anything like that, or surjective. And so let's maybe look at a few examples. Oh, so first, I would just say that whenever there exists a homomorphism from G to H, we write G arrow H. So this just means there exists some homomorphism from G to H. So what's an example of this? Well, we can take this 7 cycle, okay, and we can map it to a 5 cycle, essentially by taking a path of length 3 and kind of folding it up into just a single edge. So we get something that looks like, I'm just going to redraw the graph, but in a way where the homomorphism is evident. Okay, so here we have, it's still a 7 cycle, and sort of I can imagine that, you know, these two vertices get mapped to a single vertex in a 5 cycle, right? And these two vertices get mapped to a single vertex in a 5 cycle. And then these all get mapped to a single vertex in the 5 cycle, right? So we're sort of collapsing this path of length 3 down to a single edge. So that's one example. There's another example that probably anyone that's done a class in graph theory has seen already, and that's colorings. So a K coloring, let's say, of a graph G is a homomorphism to the complete graph on K vertices. And why is this so? Well, if you know what a K coloring is, this is just an assignment of K colors to the vertices of your graph so that adjacent vertices get distinct colors, which just means that I'm mapping the vertices of my graph to some set such that adjacent things get mapped to different things. And different in this graph is the same thing as being adjacent. Right? So that's the same thing as a homomorphism to the complete graph. Everyone that's familiar with graph theory is probably familiar with this, so you've already seen lots of examples of homomorphisms already, even if you haven't really studied them very much. And of course, you can use this to define the chromatic number of a graph. So this is, of course, the minimum number of colors it takes to color the graph properly. But in terms of homomorphisms, we can write it's the min K such that G has a homomorphism to K sub K. So easy with these. Ooh. All right. Okay, and then another example are cliques, a complete subgraph. So a graph G has a K clique. This means it has a subgraph, a subset of K vertices, which are all pairwise adjacent. And that's if and only if the complete graph on K vertices has a homomorphism to your graph. Right? You can imagine, let's just look think of a triangle, right? If I want to map a triangle, a K3, to my graph G with a homomorphism, well, all 3 of these vertices they're all adjacent, right? So that means that these 3 vertices have to get mapped to 3 vertices in G that are all adjacent to each other, which means I get a 3 clique in G, and similar for larger values of 3, right? Okay, and then again, I can define the clique number, right? This is this size over the largest clique in your graph. I can define that in terms of homomorphisms. Now it's the max such that K sub K has a homomorphism to G. Right? And I mean, okay, these are the two main graph parameters that we're going to be working with. While also taking the complement, we can get the independence number of a graph, right? If I take a clique and the complement of a graph, it's the same thing as an independent set. But you can also define lots of other sort of interesting graph parameters, like you know, fractional chromatic number can be defined in terms of homomorphisms to Kneser graphs. And there's something called circular chromatic number, which can be defined in terms of homomorphisms to a certain family of Cayley graphs or circulants. So it's just maybe a nice framework to sort of unify all these different graph parameters. And another nice thing about homomorphisms is that they compose. So if I have F1, which is a homomorphism from G to H, and F2, which is a homomorphism from H to K, then I can compose them. So I take F2 composed with F1. This is a homomorphism from G to K. And this is straightforward, right? I mean, if I take two adjacent vertices in G, right? I first apply F1, so that means I get adjacent vertices in H, and then I apply F2, and then I will have to get adjacent vertices in K, just by the definition of homomorphism. So we can compose them, and so you can get some sort of like, I guess, category if you're into that sort of thing. We can write this as if G has homomorphism to K. This is sort of less specific because this is just as existential, right? If I write G has homomorphism to K and H as a G has a homomorphism to H and H has a homomorphism to K, then G has a homomorphism, right? And already using this, you can see very quickly that if I take if G has a homomorphism to H, then the chromatic number of G has to be at most the chromatic number of H, right? Because I can define this chromatic number in terms of having a homomorphism to a complete graph. Yes, do you have a question?
Yeah, on your top line there about the K group, are you assuming that it's injective, like 1 and 1?
It will have to be injective in this case because I preserve adjacency, and a vertex is not adjacent to itself.
I see. Okay.
Yeah, I probably should have said that, right? I mean, in general, it doesn't have to be injective, right? I mean, for instance, this example with the odd cycle, the 7 cycle to the 5 cycle is not injective, but I don't consider a vertex to be adjacent to itself unless maybe it has a loop. But if I'm not allowing loops, which with homomorphisms, the loops kind of, at least in terms of existence, make things trivial. Because if you have a loop, then anything has a homomorphism to you. And then if you don't have a loop, then no graph with a loop has a homomorphism to you. If you have an empty graph, then it has a homomorphism to anything. So by empty, you mean no edges. Yeah, exactly. It can be very easily non-injective, right? As least injective as you like. Okay. Right. So you get that you get this inequality, right? Because if G is a homomorphism to H, right, then now H will have a homomorphism to a complete graph of this size, right? And now G has a homomorphism to H, so it will also have a homomorphism to a complete graph of this size, right? But I take the min for the chromatic number, right? So that means this will have to be at most this. And similarly, you get the clique number. It's the same sort of argument. Also for like fractional chromatic number, you get the same thing. So you get that these are what I would call these homomorphism monotone parameters. Okay, and with these, it's sort of kind of obvious because I can define them in terms of homomorphisms, but there are examples of other parameters that aren't defined in terms of homomorphisms that they still have this nice property of being homomorphism monotone. We'll see that later. Okay, so that's sort of just a very brief introduction to homomorphisms, but we want to define a quantum analog of this notion, right? And the way we do that actually is we kind of encode this notion of homomorphism into a certain type of game. Actually, oh, there are 3 boards. Okay.
One doesn't like to stay up.
Okay.
So we move it in.
This one, no wait, this one doesn't move. This is the back.
The one in the middle is going to move down.
So if I move it at all, it's going to move down. Maybe I should just.
That one's unstable. The one in front of you is very stable.
This one is very stable. Yes, this is attached to the wall, I believe. So hopefully stable. Okay, I'll just do this one and the front one. Okay, so we need to kind of encode this notion of homomorphism in a game, and the way the game works is you have sort of three parties. One you might call a referee, or sometimes you call it a verifier. And actually, maybe can everyone see if I write? Yeah. You can still see. Okay, good. Okay, so you have a referee or a verifier, and then you have two cooperating players, Alice and Bob. And what happens, so I should say, this is for two graphs, G and H, this is the GH homomorphism game. We're going to abbreviate homomorphism with just hom because I'm just lazy. And the way this game works is that the referee is going to send a vertex of G to Alice. We call this little g sub A, and a vertex of G to Bob, and we'll call this little g sub B. And Alice has to respond with a vertex from H. Let's call it H sub A. And Bob is going to respond also with a vertex from H, and we're going to call that H sub B. Is this too small? I can write bigger. It's okay? It's okay. Everyone's got better eyesight than me. Okay. So this is sort of the format of the game. The referee sends a vertex from G to Alice. She responds with a vertex of H, and similarly for Bob. They could be the same vertex or different vertices, it doesn't matter. And Alice and Bob, as I said, they're kind of cooperating, and they want to sort of win. What does it mean to win? It means that they need to satisfy two conditions. So the first one is sort of a consistency condition. So if they're given the same vertex, they must respond with the same vertex. Okay, you can think of this as like, I mean, when you were in, I don't know, like middle school or high school or something, there's this vertical line test for functions, right? There's a function means that for every one input, you get one output, right? So this is sort of what this is saying. Okay, and then the next condition, right, is the thing that encodes this homomorphism notion, right? So if the vertices that they receive from G are adjacent, then the vertices they respond with better be adjacent. And the trick is that during the game, Alice and Bob can't communicate with each other. So they can agree on a strategy before the game begins, and they know what the graphs G and H are, but they don't know what vertices the referee is going to send them. Right? And even after the game starts, Alice doesn't know what vertex Bob receives. Right? If they somehow knew which vertex the other person received, it'd be trivial to win the game, right? But they don't know that. And we really want them to win kind of regardless of what the referee sends them. You can think that, okay, maybe the referee sends vertices with some uniform distribution, and we want them to win, say, with probability 1. Right? They need to come up with some strategy that allows them to win probability 1. So you could think that they just kind of play one round, right? So they just get one vertex. If you want, you can think they play many rounds. That's also fine, but just remember the referee doesn't remember their answers from the previous round, right? Otherwise, the referee can just send them all the vertices, right? And then it's sort of trivial. Okay, but so what happens with this game? Well, what happens if there is a homomorphism from G to H, right? So if F is a homomorphism from G to H, right? Then all I need to do is I let HA equal F of GA, right? And HB equal F of GB. Okay, and now, well, of course, this first condition holds, right? Because, I mean, if GA and GB are equal, then of course HA and HB are going to be equal. And also, since F is a homomorphism, right? If the two vertices were adjacent, right? Then HA and HB will be adjacent, just by the definition. All right, so if you have a homomorphism, then you can win this game, we say perfectly or with probability 1. And it turns out actually the converse is also true. So you can actually win the game if and only if, well, we can win the game perfectly with the classical strategy if and only if there actually is a homomorphism from G to H. Now I'm being a little hand wavy here because I haven't really rigorously defined what it means to have a classical strategy. And I don't really want to go into much detail about that, but in the simplest case, we can imagine that Alice and Bob are restricted to doing something completely deterministic, right? And since we require that they somehow don't know what the other one's input is, this deterministic thing that they do, it can only depend on their input, which means they just have a function from their inputs to their possible outputs. Okay, and the first condition says that the function for Alice and the function for Bob is the same, and the second condition says that the function has to be a homomorphism. Generally, you in the classical strategy, you would actually allow them to have some sort of shared randomness, so they have some like access to some random variable that could take some value with certain probabilities. But since we want them to win perfectly, this doesn't really change anything. It just means that they're sort of taking a convex combination of these deterministic strategies, right? And if they take any deterministic strategy that doesn't win perfectly with some non-zero weight, then they'll lose with some non-zero probability. Yes.
I know this is a dumb case, but what's to prevent them from just agreeing beforehand to just always send this one fixed page?
Like a fixed vertex.
Yeah, all the time.
Well, when if they get adjacent vertices from G, then they lose.
Oh, adjacent. Okay, I got that.
Mm-hmm.
That's it.
Yep.
Thank you.
No problem. Yeah, I mean, as I said before, like if they somehow knew what the other person was given, right, then they would say, "Oh, were we given the same vertex? Let's pick some vertex from H and respond with that. Were we given adjacent vertices? Oh, well, let's pick two adjacent vertices from H and respond to that." But they don't know.
Yeah. So just to repeat the question for the online audience.
Oh, yeah.
So that what's preventing the referee from just sending one vertex to the A and B ring?
I think the players from always responding with the same vertex. Yeah, yeah, and that's because they lose if they get adjacent vertices. So this is really captures the notion of homomorphism in the sense that you can win this perfectly if and only if there is a homomorphism G to H. And so this motivates our definition of quantum homomorphism. So we consider the same game. The game is not going to change. The game is always, there's nothing quantum about the game really, right? But now we allow them some bigger class of strategies, and particularly we allow them to use quantum strategy. So let's talk about quantum strategies. To be specific, this is a quantum strategy in the sort of, there's essentially two kind of frameworks for quantum strategies for this type of game, because there's two frameworks for sort of joint measurements on like measurements on a joint quantum system. So there's a tensor product framework and then the commuting operator framework. So let's start with the tensor product framework. That's a little bit, well, they're not really that dissimilar, but maybe this is the more common one. Strategies. Okay, and so what is a quantum strategy for this game? Okay, so now what they're allowed to do is now instead of having access maybe to some shared random variable, now they have access to some shared quantum state. Okay, so it can be some entangled state between the two parties, and they're allowed to make local measurements sort of on their part of the state. Right, so what exactly does that mean? So I guess everyone is okay with bracket notation based on the first talk, right? So, okay, so we have some quantum state, which is just some, it's some unit vector, and it's going to be in this tensor product space. So let's say CDA tensor CDB. Okay, so this is isomorphic to C to the dA times dB, of course, right? When we think of it as this having this tensor product structure, and this is a unit vector. Okay, so this corresponds to the shared entangled state that they have. Well, I guess strictly speaking, it doesn't have to be entangled, but if it's not going to help them do anything better than classical, right? And then for every input that Alice could get, she's going to have some quantum measurement on her part of the state. So that means there's some, let's call it wavy E sub G, which is just, this is a collection, or I guess I should say tuple, if I want to be really rigorous, but I won't be, okay? This is some collection of these matrices for all H. So these are matrices. I should have said, actually, is there an eraser other than my hand that I can use? I should have said. So this is a matrix. This is going to be a dA by dA matrix.
Is dA predetermined? You're going to be minimizing that later.
No, we don't care about it can be whatever they want them to be, right? There's some parameter that they get to choose, right? Like same as choosing the state or anything like that. Right? Okay. Yeah, I mean, there's certainly a question you could ask: what is the smallest d? that you can use, but I don't know of any results along that. So we have this EGH for every, this is for every H V of H. What does it mean for this to be a quantum measurement? I need not just that this is some matrix. I actually need that these are positive semi-definite. Which I write like this. Okay, and I need that when I sum them up, I get identity. Okay, and this is a quantum measurement, or I guess specifically this is known as a POVM, a positive operator valued measurement. But it's just a collection of positive semi-definite matrices that add up to identity, right? And I have such a thing for every possible input for Alice. So this is sort of the collection of Alice's measurements. And then I have the same. No, I have the same for Bob. He has some measurement for every possible input. Call them FGH. All right, so that's all sort of the parts of the quantum strategy, right? They have the shared entangled state, and then the way it works is now Alice is going to get her G sub A, right? And that G sub A corresponds to one of these measurements. She performs that measurement on her part of the shared entangled state, and she's going to get some outcome, and the outcome just means she gets some index here for these operators in the measurement, right? So she gets some vertex of H. And that's what she responds to the referee with, right? I mean, you can imagine, you could think that, oh, maybe she wants to do some measurement, and then she does some like post-processing where she takes the measurement value and decides to do something based on that, but that can all somehow be incorporated just into the measurement itself. So there's no need to do that. Okay, so that's sort of, I guess, physically what is going on here. They're doing these quantum measurements, whatever that means. They hit some buttons on some machines in some lab, right? And they get some outcomes. Mathematically, I keep trying to move this up. Okay, so mathematically, what's going to happen is that they're going to get some outcome, but it's not going to be a deterministic strategy, right? It's going to be some probabilistic strategy. Okay, so if I let P of H comma H prime given G comma G prime, I'm going to, this is defined as the probability that Alice and Bob respond. Okay, now I'm realizing that I should have used this one first. Respond with H and H prime given, so it's a conditional probability, they were sent G and G prime. So for every possible pair of inputs, right, they're going to have some probability distribution on the outputs. Okay, and that gives this P of H comma H prime given G comma G prime. All right, and you can write down the formula for this probability in terms of this state and these measurements, and it's just the following. It's going to be. Can people read this, or is this too low? It's visible online, but can everyone in the audience see it? No, you can't see it. The computer's annoying. The computer's annoying. I probably don't want to close that. I don't know what will happen. Right? All right, I'll write it here. Okay. Yeah, but then I have to cover this up. Maybe I'll just reuse one of this one. Okay. So this probability then is equal to psi, and then all right, so we just take the tensor product of the measurement operators, right? Sort of the measurement operators corresponding to Alice receiving G and getting H as an output, and Bob receiving G prime and getting H prime as an output. Take the tensor product, and then we sandwich that by this shared state psi. Okay, and well, this really is going to be a probability distribution. First of all, this is going to be non-negative because these are PSD matrices. And it's going to sum to 1 because if I fix G and G prime, I sum over H and H prime, right? Then I can bring that sum inside, and I can actually bring the sum over H just to this part and the sum over H prime just to this part, right? And then I get identity and identity, right? And then this is a unit vector, so I just get a unit vector's inner product with itself, which is 1. Right? So I really do get a probability distribution. How am I on time? Okay, still half an hour. All right, so that's.
Sorry.
Yeah.
Do I correctly understand this is what it means, the quantum version? This is not This is not how you haven't told us how the game is played, right?
Well, no, I'm saying that,
We're gonna find this POV.
yeah. I mean, the game is played. Alice gets some little g, and she does this measurement, right?
Mhm.
So she, for a fixed g, she has a whole collection of these operators for every little h and big H, right? She applies this measurement on her part of the quantum state, whatever that means, right? And Bob does the same thing with
But
these.
this is the requirement. This is not the strategy yet, is it?
The strategy is these set of measurements in this shared entangled state, right? And when they do this, they get outcomes according to this probability distribution.
But can't they just run this thing multiple times and then output the majority?
Why would they? They don't want to run it multiple times. What does it mean? I mean, well, first of all, they can't. They would need multiple copies of the state, I guess. But
Yeah.
I don't think running it multiple times is not going to help them.
Yeah, but okay. So
Uh.
this probability will be 1 that is correct?
Well, no, that's the trick. You want to find these measurements in this state so that the probability that you win is 1.
But
Right.
I'm saying that suppose you're not able to find that, but you're able to find some matrices, EIs, FIs, such that the probability is like over half.
That
Then
you-
couldn't you just reconstruct the state many times, execute it like 1,000 times, and then still?
No, I don't think that will work, right? I mean, so you want to just do it a bunch of times.
Yeah.
And then you take the thing that appears the most.
Yeah, so suppose that you're guaranteed that more than half the time you would get the correct vertex. Okay.
I mean, that might. I don't think that this helps you. So I've never thought about this, so I don't know what exactly would happen if you did this, but I don't see why that would help you. I mean, you know that you would, first of all, somehow whether they win or not, it doesn't depend on just a single person. It somehow depends on like how the pairs of inputs and the pairs of output relate, right? So, and they don't know what the other person is getting when they do these measurements, so they can't pick the majority of the ordered pairs of outcomes,
I see.
right? They can only pick the majority of their single outcome anyways, right? Which might not be the thing that appears in the majority of the ordered paired outcomes, right? But maybe that's the reason why the whatever argument you were thinking of doesn't work.
Okay.
I don't know. I never thought about that before. Okay. Right. Okay. So this is the probability that they answer with H and H prime, assuming that they were given G and G prime. And let's see. Since I still have about 30 minutes, I think. No, maybe I will. Okay, I will just briefly say, so this was quantum tensor strategies, right? And there's also another thing, so quantum commuting strategies, okay? I think it's a bit of an odd word, because usually in quantum, when everything commutes, you just do classical stuff. But this is not that kind of commuting. Not everything commutes is the issue. So quantum commuting, I would just sort of say what the differences are, very briefly. Just because, I mean, for homomorphisms, we're going to be mainly focused on the tensor strategies, but for isomorphisms, the commuting strategies have nice things going on. So it's good to know what those are ahead of time. All right. And like we usually use like QC to abbreviate this and QT to abbreviate this, although most people would use just Q. But I want to be clear, I guess. It's a difference. You still have this psi unit vector. But now it can be in an arbitrary Hilbert space, right, which means it can be infinite dimensional. Actually, I could have also allowed infinite dimensional spaces over here. And for this game, it won't make any difference. And so we might as well stick with finite dimensional things, because probably people are more comfortable with that. But here, you really do need to allow infinite dimensional spaces. Otherwise, this actually collapses to the tensor product thing. Okay. Okay, so this is some arbitrary Hilbert space, and now we have these measurements, but there's no partition of the space here, right? Before we kind of had a partition of the space, there's a CDA and a CDB. Here, there's just one space, and then we have that these EGHs and the FGHs, right? These are bounded linear operators on H. right? So they're sort of living in the same space, like the E's and the F's. And of course, they're also, they're positive operators, and they have this summing to identity condition, right? Okay, also for F. But now, since I don't have this tensor product structure, I want to require that all of Alice's operators and all of Bob's measurement operators commute with each other. So that's why it's called quantum commuting. All of Alice's commute with all of Bob's, but Alice's operators don't have to commute with themselves, and Bob's operators don't have to commute with themselves. If they did all commute, then you wouldn't get anything that's not classical. Okay, so that's why it's called quantum commuting, and it's it's just that Alice's. You can think that these living in some sort of sub-algebra, and this is in some other sub-algebra, which is commuting with this one, I guess, if you want to be, I don't know, weird about it. Okay. And now this probability, it has to change, right? We don't have this tensor product here. If we took a tensor product here, right, then we wouldn't be in we wouldn't be able to sandwich it with psi anymore, right? Psi lives in H, right? So you actually just take the usual product, right? So in this case, we have that this is the usual product. Okay, but everything is okay because since these commute, actually, you still get this as non-negative. Okay, they're PSD and they commute, so actually the product is PSD. So this is non-negative, and again, if you sum over all H and H prime, you get that, and you bring the sum in, you get identity here, and so you just get one. So you do get a probability distribution still.
So the one is a special case where Alice tensors everything with identity and Bob tensors.
It's exactly what I was going to say next. Yeah. So to go from like a QT strategy to a QC strategy, like if I have my EGH here and my F G prime H primes here, right? Then I just go to, right? And so now these are acting on the same space, and they of course commute with each other. Okay. So this is really kind of a special case of this thing. But as I said, if you restrict to finite dimensions, then these are equivalent. This for the homomorphism game, at least, like it doesn't matter if you use infinite dimensions. So we might as well stick with finite dimensional things.
I guess you want some E's and F's to be orthogonal when some edges exist or something.
Yeah, that's what we're getting to. So I said we want to win with probability 1. Well, what does that mean? It just means we want to lose with probability 0. So that means we want this P of H comma H prime given G comma G prime equals 0 if we would lose on these answers for these questions. So meaning if G equals G prime and H is not equal to H prime, or G is adjacent to G prime and H is not adjacent to H prime. And of course, we can write down the formula for this, right? This is, again, it's just this. Now we go back to the tensor product framework. Just want some of these things to be equal to 0, right? And being equal to 0 is like at least somewhat combinatorial, right? I mean, as opposed to just being like small or something, right? And that's what makes this kind of nicer. But because of this, you can get a nice reformulation, which I'm just going to give the theorem and without the proof, and then we can just use that sort of as our definition if we want for quantum homomorphism. So, and this theorem is that I didn't define quantum homomorphism, but it's obvious what the definition is, right? So I mean, definition. I will write G as a quantum to H, which I denote by, again, I should say quantum tensor, right? So we write the same notation as before, but we add this QT on top of the arrow, okay? If the GH homomorphism game, a perfect, I'll just say QT strategy. And again, what this means is perfect just means you win probability 1, which means that these things are 0, right? So I need to find some vector and these PSD matrices such that the appropriate things are 0. But that's kind of a lot of stuff, right? I mean, I need the vector, I need matrices for Alice and matrices for Bob, right? So I'd like to reduce sort of the complexity, so to speak, of sort of like what we actually need to look for. Okay, and for that, we have this theorem, and it says that G has a quantum homomorphism to H, if and only if there exist projections. So when I say projections, I mean orthogonal projections. So Hermitian and squares to itself. Okay, sort of E, G, H, where G and V of G, and H and V of H, such that the following holds. Okay, the first thing is that if I fix the vertex from G and I sum over H, I get identity. I guess I should say this is some D by D matrices. D can be whatever we want, we don't care.
You don't require X, you just require.
So I don't require.
There's two players, you can only require the E system.
Yeah, it turns out that actually, like, once you can find these, then you can construct the other ones. Right. Also, like, if you have any strategy, then sort of up to some kind of like transformations. Essentially, what you have is the stuff I'm about to write here, and then the F is just a transpose of the E's, and this is maximally entangled state. Oh, that's up to some hand waving. Okay. And the other thing is these orthogonality conditions that Crystal was getting at. Okay, and maybe, I don't know, some of you maybe will notice that actually I'm being a bit redundant here. Okay, if I have projections that add up to identity, okay, they have to be mutually orthogonal, right? So actually, this condition here I don't really need, but I like to write it anyways, just to be just point out that you do have those orthogonalities, right? But we do need this. We can't. That's not implied. Okay, and so now, okay, we've reduced it, so we only have. Now we know that we have to look for projections for one thing. We don't have to worry about the state at all, and we only have to look for these E's rather than the E's and the F's. So that makes things a little bit nicer. Of course, it still doesn't make anything particularly easy, but it is I mean, maybe it's a little bit easier to think about, right? I mean, now this is more or less just an algebraic kind of definition. I don't need to think about quantum measurements if I don't want to. Right, I'm trying to find some projections that have some nice properties. Right, okay, so now 15 minutes left. So I want to point out that these are also composable. So if G is a quantum homomorphism to H and H is a quantum homomorphism to K, then G has a quantum homomorphism to K, right? And the proof, okay, so I have a quantum homomorphism from G to H. That's going to give me some E, G, H's. And then this is going to give me some, let's just say F, H, K's, right? That satisfy these conditions over here. Okay, and then I define P, G, K. This is the sum over H of E, G, H, tensor F, H, K. Right? And this maybe looks a little bit like matrix multiplication, right? Of something over H, except I have tensor product instead of the usual product. Okay, and then I will just leave it as an exercise. It's sort of very straightforward to show that this gives a quantum homomorphism from G to K. You can also argue in terms of just the game itself if you're comfortable with that, right? I mean, if I have a quantum homomorphism from G to H, it means I have this quantum strategy for the GH homomorphism game, and similarly for the HK homomorphism game. So if now I want to play the GK homomorphism game, what do? I pretend I'm playing the GH homomorphism game to begin with. So I get my vertices from G from the referee. I pretend I'm playing the GH homomorphism game, so I get a vertex from H out of that. And now I pretend I'm playing the HK homomorphism game using those as my inputs, and I get a vertex from K. I respond like this. Doesn't depend on the class of strategy you're using. Works for classical, quantum tensor, quantum commuting. I guess you need to be a little careful about sort of like what types of things are allowed in a strategy, but it's not so important. All right, so you can compose these things. That's quite nice, right? That's sort of, I think, what makes it nice. Yes. Okay. Yeah. So I'll leave that as an exercise. Like I said, it's straightforward. It's just not hard. But what I want to do now is I want to take the conditions from this theorem, and I want to kind of encode them in a slightly different way. So essentially, I want to get like a reformulation of this statement, where I'm assigning some projections to vertices in some graph. Okay, so it's going to be some product graph. So I will need to encode these orthogonality conditions. This will have to do with adjacency in the graph, and then I would have to come up with some way of encoding this as well. This will be by kind of maximizing some parameter. So we take the this is going to be called the homomorphic product. Okay, and I'll just denote it like this. Okay, and the vertices, just the product of the vertex sets. Okay.
The camera is only getting like as far as the vertical line in the P improves.
Oh. Oh, okay.
You just move over a couple inches.
Okay, so the vertex set of this product is just the product of the vertex sets, and then I'm going to have that an ordered pair of vertex in this product. It's adjacent to another vertex. Right, essentially, just if this holds, right? So G is equal to G prime and H is not equal to H prime, or G is adjacent to G prime and H is not adjacent to H prime. So one thing this means is if I fix the first coordinate and I vary the second, I get some clique. So that's just the definition of this product. And now I want to sort of define some notion that's going to correspond to assigning these projections to the vertices in this product. So I defined a projective packing of G. So what is this? This is just an assignment of projections to the vertices of my graph. So this is going to be a D by D projection, such that adjacent vertices receive orthogonal projections. So you can see if I have this set of projections, as in this theorem, it gives me a projective packing of this homomorphic product. The converse is not true, of course, because I can assign the zero projection everywhere. Right? By the way, I should point out this is like a relaxation of independent set, because if I take independent set in my graph, I assign identity to all those vertices, and I assign zero everywhere else, then it will give me a projective packing. Okay, so I need to somehow I've kind of encoded this part. I need to somehow figure out what to do with that. And so I guess I only have, am I supposed to finish 5 minutes early? Then I will define the value of a projective packing. And that's going to be the thing that we want to maximize. So the value of a projective packing, this is just the sum of the ranks of all the projections, but I should divide it by the dimension that they live in, right? Otherwise, I can just pencil them all with identity and get arbitrarily big rank, right? So I need to somehow normalize it. So this is the value of a projective packing, and you can see this example with the independent set. What's the value? Well, I have an independent set that I assigned identity to all of them, so all of those have rank D. If I get D times the independent set, when I sum the size of the independent set, when I sum up the ranks, I divide by D, I just get the size of the independent set. And so then the theorem is that G has a quantum tensor homomorphism to H if and only if this has a projective packing of value of vertices in G. Right? The reason this works out is that, remember I said when you fix G and you vary H, I get these cliques in my graph. So for a projective packing, all the projections assigned to the vertices in one of those cliques have to be mutually orthogonal. So if I were to, so that means that they sum up to some projection, and the sum of their ranks is at most D, right? So if I take this sum over H, the rank of E G H, this is at most D, because these all have to be mutually orthogonal. and is actually equal to D if and only if the sum of these projections is identity. Okay, that's a short little linear algebra lemma. Okay, and so that means that if I can get a projective packing of value D, then actually for all of those cliques for each little g, I have to get equality here, which means I have to get equal to identity here. Right, and conversely, if I have equal to identity, then of course the sum of these ranks is equal to D. Okay, and so up to some details. This is the theorem, and I guess I will also I'll just briefly mention that I can also define the projective packing number of a graph, which I write alpha sub p, and this is going to be the supremum of the values of a projective packing of G. Okay, we need to take supremum, or we don't know we can take max because there's no guarantee that somehow you can actually attain whatever the supremum is. Right. So I could rewrite this theorem. I can almost rewrite this theorem as saying that this holds if and only if alpha p of this is equal to the size of G, but it's not quite right because I actually need that it's attained. Right. Okay, so I'll end there.
So is the goal of the area to
Characterize those pairs of G and H for which such a thing exists?
I mean,
or,
it's undecidable, so there's no hope of that, I don't think.
okay, or to construct examples of them for which they.
Yeah, I mean, okay, so you shouldn't really define something and not give an example. The problem, I guess, with this is it takes a little bit of work to give the example. So that's what we'll do the next two lectures. We'll talk about some examples. I wouldn't claim to know what the real goal of the area is. I mean, for me, I think what is interesting is that it makes connections to a lot of different areas, and that's what seems to be what other people like about it. Like, you have this kind of now like a quantum analog of this category, right? I mean, this is some arrow between objects, right? And you could talk about some sort of quantum category of quantum morphisms, and people that do category theory like that kind of thing, so they talk about that. Then you can also consider some kind of semi-definite relaxation of these quantum homomorphisms, and then you can get into some conic programming and what people that do conic programming like that. There's more connections, but I mean I think that's really the sort of idea, especially for the homomorphisms. There's not like a big theorem for the quantum homomorphisms or something like that.
So I'm looking at this theorem in the lower left. And so, I mean, to me, at least from my background, what this is saying is like, yeah, so for each G, I mean, we have something that is, this set of mutually orthogonal projections. So we could think of this as a certain way of like binning an orthonormal basis. And so the kind of the real thing is how once the G's are no longer fixed and we're looking at cross G's, how they interact. So could this be seen as like a generalization of mutually unbiased bases, where it's like you have these orthonormal bases and the important thing is like how these things interact with each other, and that gives us the structure that we need?
I mean, I guess I can't say. I don't know a lot about MUVs. I mean, I know that you want that for any vector in one, the inner product of the vector, and another one is some fixed thing.
No, it's like.
I don't like giving very definite answers, right? So, I mean, I think not exactly, but I mean, it certainly is about sort of how these projections. I mean, you're right that it's like, okay, you have a set of like projections that sort of decompose the identity. Right, and it matters how these different sets interact with each other. That is true, which is similar to MUBs, right? But I don't know if there's really more of a connection than that.
I guess my question would be if there would be some classical sort of graph structure, I don't know, because I don't quite yet have a good enough feeling, but some sort of type of graph structure that would like induce these things to be like MUBs.
Okay, I can't say, but I don't think I have an answer. Maybe no, but I wouldn't want to claim no, since I don't have any sort of proof that you can't do such thing.
So in general, they don't have to have the same dimension.
What do you mean? Well, I mean, for a given like selection of the projections, they all have some dimension, but
they don't have the same range. Like the range.
oh yeah, they don't have the same rank. They don't. No, yeah. I mean, you could have a lot. Probably with the constructions that we're going to see, a lot of them are going to be 0 or something like that. Well, that's depends on what constructions you want.
Isn't it that you get a point in this case?
I don't know what a frame is, so I mean, maybe. For colorings, all the constructions, I think that for colorings, essentially all the constructions are known, you just rank one things. And then you get bases, but it's not mutually unbiased bases, right? Something else.
Still has a question.
Yeah, because the fact that with projections and not just positive operators, then that means because if you have explicit and not scale projections, you get to something identity. Like you're getting something orthonormal, so you can't get something that's redundant, which is why he said that first thing, the orthonormality is like forced upon you, because you're not allowed, it's not just positive semi-definite, but it's explicitly orthogonal projections, and we have those come to the identity, then you can't get sort of redundancy in some sense. So if everything's rank 1, it has to be orthonormal basis.
So just following up on Matt's question, can you just give us some anchors? Like, is this in this general framework or some special cases, quantum coloring, quantum?
Yeah, okay, so what we're going to talk about tomorrow are quantum independent sets, or equivalently like quantum cliques, but I guess just historically people talk about quantum independent sets rather. And then actually the thing that came before quantum homomorphisms are quantum colorings. That was defined first by Cameron, Montanaro, Winters, Severini, and I'm sure I'm forgetting another one, but Newman. Oh yeah, I should have probably remembered that one. He's not here. So yeah, so they define quantum colorings, right?
So this is a general framework that contains.
Yeah, I mean, it's sort of a straightforward generalization. Once you see quantum coloring, if you know what a homomorphism is, okay, you just define it. But the thing that's nice is somehow, okay, you have this composability, and it sort of like gives you the kind of like a bigger kind of, I don't know, like kind of zoo or something, right? Of things happening, right? I mean, with colorings, you just have the coloring of a graph, right? Now you can compose things, and you have this kind of category structure. So, but all the known, essentially all the known constructions are for independent sets or colorings. Right? There's not really a genuine, as far as I'm aware. I mean, I'm sure you can construct something that isn't a coloring or independent set, right? But it's going to be using one of those two things to do it, right? Yeah. So.
Thank you.
Maybe I don't understand something well, but behind this there should be receipt to build the state side.
Sorry, say it again.
I wonder if behind the proof of this theorem is there a receipt to build the initial state side, which is
what's going on behind the proof of this theorem?
the initial state.
Where does it go?
You have to choose in a special way.
So essentially, again, this is waving away some details. Essentially, this ends up having to be a maximally entangled, this shared state that they have. It has to be a maximally entangled state.
So the theorems the proof of the theorem should have a way of building this.
Yes, okay, if you take projections that satisfy this, you use the E's for the E's up here. For the F's, you just take the transpose, and for psi, you take maximum entangled state. It's the, I mean, you fix the dimension, and then it's, sum of I tensor I. I mean, you can take, it needs to be like the I, like the first base, the basis for the first space and the basis of the second space, I guess should be the same. Otherwise, you need to do some unitary thing to the F's.
Okay, I have a less intelligent question. What does it mean to have the infinite dimensional Hilbert space in terms of implementation? You have infinitely many qubits or something?
I don't know. I don't know. Or care. Don't care. Ask Laura.
There's some of these visual systems, right? Their corresponding space is infinite dimensional.
I mean, I guess in this continuous variable thing, but that's not really what is it?
If you think about it in terms of Hamiltonians.
Yeah, I mean, I don't, but if you want to do that.
Any more questions? Okay, let's thank David again.